Hello.
Hello, sir.
আমি কই?
Sir, আসেন sir.
আচ্ছা। So I actually stopped the recording to have that as a different video and starting the subject material lecture with a different video, যাতে করে পরে ইউটিউবে আপলোড দেওয়ার সময় আলাদা আলাদা ভিডিওগুলো আলাদা আলাদা থাকে। সো ওটাকে ইন্ট্রোডাকশন হিসেবে ইন্ট্রোডাকশন হিসেবে আপ করব, আর এটা আপ করব হচ্ছে মেজারমেন্ট টেকনিকের লেকচার 1 হিসেবে।
Sir, can I ask something?
বলো।
What was your cat's reaction upon seeing your daughter?
They don't live in the same house.
Oh.
Cats are at coaching. Cats are exclusively at coaching.
Oh, okay, sir.
কে আসছে? আচ্ছা, ভাইয়া বেড়ে গেছিল, ভাই আসছে, সমস্যা নাই। অলরাইট, সো লেটস স্টার্ট। প্রথম জিনিস হচ্ছে যে whenever we do some measurement, every measurement has a level of reliability. Level of reliability in a sense, and let me give a gross example to make sense with you. For example, if I try to measure my height, the amount of hair in my scalp really doesn't matter. I can take my height measurement with a lot of hair. I can take my height measurement with bald headed. It would still be the same. But you do understand that in terms of thickness, my hairs do have some measurable thickness. But for the case of my height, that hair thickness really doesn't make much of a difference. So that can be considered within the range of acceptable errors. So this is a very important idea, the range of acceptable error. Similarly, let's say if this is the earth and this is me, figure not drawn to scale. If the radius of earth is measured, let's say, or the diameter of the earth is measured, let's say from one side all the way to the next side, this diameter can be measured up to my feet, this diameter can be measured up to my head. These two measurements for the case of the diameter of the earth would not make much difference. I mean, if you actually measure into meters, you might have some really big amount of numbers, and this might actually affect the value at the 7th or the 8th significant figure. So we can consider my entire height to be of negligible significance for this scenario. Once again, if you try to measure the orbital radius of earth, for example, let's say this is the sun, this is the orbit of the earth. I'm drawing a horizontal orbit, so let's say the earth is going around in circles like that. Then the orbital radius, this is the earth is over here, so the orbital radius would be from the center of the sun all the way to the center of the earth. Now in this case, the radius of the earth can be considered to be negligible as well. So whenever we try to measure something, it all comes down to the point that our measurement has to be accurate, or measurement has to have a significant acceptability with some amount of error involved. This is equally true for our measurement instruments as well. For example, if you consider a basic meter rule, the smallest division in a meter rule is 1 millimeter. 1 millimeter. This is the smallest division of a meter rule, which means any measurement that you take out of a meter rule will be always coming in full fraction, in full multiple of millimeters. So if I just show you the image of a meter rule, let me just go over there. There you see the image of a meter rule. So this is the end image of a meter rule. So this is 100 centimeter mark, 99 centimeter mark, and within 1 centimeter mark you have 10 divisions. So each of these smallest division, so the gap between two closest line represents 1 millimeter. If you're trying to measure something using a meter rule, your measurements should be given in millimeters, not in a fraction of millimeter, because you cannot simply assume what fraction of a millimeter just by looking at it over here. Now, if it so happens that let's say this is a meter rule, let's say this is a meter rule, I'm giving a break sign, and here you have all the millimeter lines over here, and you're trying to measure an object with a way that you have lined up the zero over here perfectly, and your object that you're trying to measure happens to fall right over here. So let's say the object is up to this mark. Now you might wonder that which measurement do you record? Are you going to record this one, or are you going to record this one? Now this falls on your discretion. For the case of measurement of an object, for the length of an object, you can mention the length of this object as this measurement. You can also mention the length of this object as this measurement as well. But your measurement, neither of these measurements are absolutely correct, because you can see that the actual measurement was halfway between these two readings. Halfway between these two readings. Now, this is really important for you to understand that whenever we do any measurement using a meter rule, our readings can be correct up to 1 millimeter for one reading. Now, I'm going to explain what this for one reading means after a while. So if we are trying to measure anything using a meter rule, this is what we call the uncertainty. That our readings can be correct up to 1 millimeter plus or minus. So if you take a measure reading of in meter rules, so let's say if you write, let's say that an object is 631 millimeter, you can write 631 plus minus 1 millimeter of measurement. So that's the actual representation for the so this is how we can record the reading of a object's length that comes in millimeter precision, and that plus minus 1 millimeter is what we call the uncertainty of the reading. Now, this thing is also dependent upon how we record a certain length. Let me give you an example. Let's say this is a meter rule. I'm trying to draw a full meter rule over here. So let's say we have all the lengths over here. You can try to measure the length of a meter rule in length of an object in two different ways. Let's say this is a table. This is a table, and the table is attached on one side. There is a wall. So this is the top of the table, and there is a wall over here. So you can place the meter rule on top of the table. This is the meter rule. And let's say the object that you're trying to measure is attached right over here. That is also touching the wall, and the object lengths up to this much. Now you're gonna take the reading right over here, and whatever that comes up, you're gonna mention is it as the object's length. So it can be some number in terms of millimeter, and then you're gonna have an uncertainty of plus minus 1 millimeter. That's one way to take the reading. So you're actually making one observation, important information. You're making one observation to do this reading. Another alternative to measure that same object's length can be something like this. Let's say this is your table. This is a tabletop. On top of the table, you have the meter rule that is placed without the presence of any wall. And then you have the object placed on top of this object on the meter rule right over here. If you want to measure the length of this blue object using this meter rule, you're going to have to do two observations. You're going to have to take one reading right over here. Let's say this is our reading number 1. And you're going to have to take another reading right over here. Let's say this is a reading number 2. And the length of the actual object would be the subtraction of these two values. So this is reading number 2 minus reading number 1. You need to understand that this reading can have an uncertainty of plus minus 1 millimeter. And this reading can also have an observational error of plus minus 1 millimeter. You might wonder, how about we place this object exactly on the millimeter mark of one of the lines, and we do not have any error over here? The idea is that the moment we make an observed reading, it is always susceptible to this error. Making the alignment perfect on our own effort is considered to be futile. It's not going to be successful. That's the whole way how we talk about reliability. Whenever the object was placed against the wall, we did not make any observation over here. We assumed that the object's starting point was perfectly aligned with the 0 mark of the meter rule by default. And the meter rule obviously does not have any dead space. Do you guys remember what the dead space is?
जी सर
सर जीरो आगे कुछ आगे
Zero
खाली
आगे
पड़ता
zero आगे किसी space आता है. So in this case, we are assuming that there is no dead space for the meter rule, and we are not making any observation over here. So that we are making only one observation exactly at the end of the object. So that's why we only have plus minus 1 millimeter of reading, and that's basically our measured data. However, if we are making two readings, so then we have to subtract. So we can have a possible error of plus minus 1 millimeter on the left side. We can make another error over here of plus millimeter over here. So ultimately, the value you're going to get over here from the subtraction, but the amount of total uncertainty is going to be 2 millimeter. Now you might wonder, we're doing a subtraction over here, so shouldn't they cancel out each other? The answer is no. Whenever we are doing measurements, the more number of observations that you make, all of these individual observations are going to add up to more uncertainty. Additional reading will always result into bigger amount of uncertainty. So errors will always be added together. More errors will always lead up to bigger amount of possible error. Errors will not be compensating. It can happen for a case of a certain experiment, for a case of a certain measurement technique. Errors can be compensating, which is a different case. But whenever we use measuring equipments and we do multiple readings, every uncertainty of every observation would get added together to give rise to a bigger amount of measurement. For example, this was the example that we are doing for the case only of a length measurement, but we can have a whole lot of extrapolation of this whole concept. Let's say you have a cylindrical object for which you want to measure the volume. Now the formula to measure the volume of a cylinder is given by pi r square L. So pi is a constant. So it's a constant, so there is no error possibility for the value of pi. So constants have constant values. Now, so you have to measure the value of radius, you have to measure the value of length. Now, it is ideally pretty difficult to measure the radius of a solid object. So we actually measure the diameter of the object using a vernier calipers or screw gauge. We can measure the diameter. So if I want to replace this equation, let me just replace the diameter by 2 whole square into L, which gives you 1 by 4 pi d square L. Now, diameter can be directly measured, length can be directly measured. In this case, the amount of possible error in the diameter and also the amount of possible error in the length, they would together add up to the amount of possible error or uncertainty for the calculated value of the volume. You need to understand that in this case, we are not measuring the volume of the cylinder. We're actually calculating the volume of the cylinder. There is a big difference between these two things. Hear me out. A calculated number and a measured number, these are not the same thing. You can, there in some cases it's possible to measure a single variable by alternatively either of these methods, but for the example that I just produced over here, that you're going to measure the diameter using a measuring equipment, you're going to measure the length with another equipment, and in this case the volume is a calculated value. It's going to have some amount of uncertainty, which I'm going to show you how to calculate the uncertainty. Whenever a square is involved, multiple quantities are involved, I'm going to show you how to work with that after a while. That's one way to go to measurement the volume. The another alternative way to measure the volume of the cylindrical object can also be by using a measuring cylinder. So let's say you have a big enough measuring cylinder within which this whole cylindrical object can actually fit into. So you have the measuring cylinder, you fill it up with some water up to a certain level. So you get this first volume, let's say V1. Then you put the whole cylinder into here, cylindrical object over here, and then the water level increases by a secondary level. So let's say this is your V2. So if we do V2 minus V1, that should give you the volume of this whole cylinder in a single measurement. In this case, you are making two observations. You're making an observation over here, you're making an observation over here. So let's say if the smallest mark of the measuring cylinder value, let's say if the smallest measurement is, let's say 1 millimeter cube, in that case, this volume of the whole cylinder would have an uncertainty of plus minus 2 millimeter cube, because you made two observations and both of them, their uncertainties are going to get added together. So that's how different measurement technique can lead up to different type of error. Does this idea make sense up so far?
Yes, sir.
Yes,
The
sir.
idea makes sense, but I didn't understand which process, the level of uncertainty is higher?
Well, that depends upon your equipments. For example, let's say if we measure the diameter of this device using a vernier caliper, so we're going to have one type of uncertainty. If we measure the same diameter using a screw gauge, we're going to have a bit more precise reading, because the typical smallest fraction for vernier calipers or slide calipers, vernier calipers vernier constant value হচ্ছে 1/20 millimeter, because you have about 20 divisions onto the sliding scale, and the minimum length on the meter scale is 1 millimeter, so that is about 0.05 millimeter. That's the smallest length that you can measure using a vernier calipers. Whereas for the micrometer screw gauge, the least count of a micrometer screw gauge is usually 1 upon not 1, 0.5 divided by 50. The reason is 0.5 divided by 50. 0.5 is the what we call the pitch of the micrometer screw gauge. That is, for those who remember micrometer screw, let me just show you. Good, I remember. So yeah, this is the micrometer screw gauge. Typically, this thimble scale has 50 divisions within it. This image is pretty large, but it's not showing up to be large. Beautiful. So this is the sleeve, and this sleeve usually has 50 divisions in it. And the way the micrometer screw gauge work, you can see that this is the main scale or the linear scale. You have the full millimeter marks on the top side, and you have the half millimeter fraction marks on the bottom side. So this is 0 millimeter, half millimeter, 1 millimeter, 1.5 millimeter, 2 millimeter, 2.5
Yes,
millimeter, goes like this. And whenever we rotate this thimble scale or the rotating scale, one full rotation, this side actually moves left by half millimeter. And in that linear progression of half millimeter of linear distance, the circular scale goes over 50 divisions. So by moving one division, you are actually moving 1/50th of that half millimeter. That's why I wrote it in this fashion, that half millimeter divided by 50, that gives you the least count for the micrometer screw gauge, which is the smallest measurable length for a micrometer screw gauge device, which happens to be 0.01 millimeter. So that's about 5 times more precise compared to the vernier calipers. So if you use a micrometer screw gauge to measure the diameter, you're gonna have one type of uncertainty. If you measure the same thing with the vernier calipers or slide calipers, then you're gonna have another type of uncertainty. Well, obviously, the device that can measure more precisely is gonna give you a much smaller amount of uncertainty. The results are gonna be within a much smaller error value, and vice versa. Equally applicable for the measuring cylinder as well. I mean, for my example, I assume that the smallest value for the measuring cylinder marks are 1 millimeter cube, but it can also be 2 millimeter cube. It's possible that some measuring cylinder can have a much bigger fraction. Some measuring cylinder can have a much smaller fraction. It all comes down to the point that with what kind of measuring cylinder do you have? It's possible that you can also have you can have a displacement can, because do you guys remember displacement can? There is
Sir, the measurement
sir,
cylinder,
sprout
an
থেকে যে-
extra thing with an
exactly
extra.
exactly
like,
there's a large
cylinder.
enough can where there is a spout over here, and we collect the extra water while submerging the object right over here, and then we collect it over a measuring cylinder. So it's possible that other than using a whole measuring cylinder for the process, we can use a displacement can and then collect the whole water in a much really precise measuring cylinder, where we might as well have 0.25 millimeter cube for our smallest fraction. It's possible. In that case, your uncertainty is going to be far too smaller. So it's not essentially, I mean, how we collect a certain data did necessarily affect what kind of uncertainty are we going to have for a certain measurement, but it is also more dependable upon the fact that what kind of equipment, how precise of an equipment do we have for our purpose, do we have access to. The more precise equipment you can use for a certain measurement, by default, better reading can you have. Does it answer your question, Yusuf?
Yes, sir.
Beautiful. So that's sort of a bit of an idea for how the uncertainty thing works for our typical purposes. And then I'm going to talk a little bit about how we can actually smartly do experiments so that we can lower this uncertainty amount of a certain measurement. You have to understand one thing, that the smaller is the uncertainty of a certain measurement, the more reliable it is considered to be. It means that it has a less fraction of error within the measurement within itself. বলো আমার দরজা যাওয়া দেয় না।
স্যার আপনার বেবি দেখি না একটু
Yes, sir.
একটু দেখি একটু ওরা ডাকেন না প্লিজ প্লিজ
কি দেখবা?
ওরা দেখবো একটু বাবুটারে
আচ্ছা
বাবু।
ওইটা আমার ভাইয়ার বাবু, ও হচ্ছে রায়ান। এখন সে আইসা আমার মাইক্রোফোন সেটআপ দেখতেছিল, হাতে হাতে করতেছিল, ওই জন্য আই হ্যাভ আইসোলেটেড মাইসেলফ। আমি টিল দ্য এন্ড অফ দ্য ক্লাস কোয়ারেন্টাইন থাকবো, তারপর আবার বাইরে হবো। পারা নাই। আচ্ছা, যেটা বলতেছিলাম যে how can we minimize the or lower the uncertainty of a certain measurement by appropriate measuring technique, এই জিনিসটা আমি একটু আলাপ করতেছি। Here is one thing. Do you guys remember how to measure the diameter of a pencil using a string? Do any of you remember this from your
জি স্যার
ইয়েস স্যার
Sir, I
সুতা
remember
পেঁচাই।
we discussed, but I don't remember how to do that, sir.
let's say you have a pencil over here and you have a string available to you and a meter rule and nothing else. You are asked to measure the diameter of this pencil. Do you remember how to do that?
ইয়েস স্যার
I'll help you remember this. The way it can be done is that we take this string and then we wrap it around the pencil very finely with the strings touching each other, not with gaps, not like that, not gaps like that. So we actually make them roll really close side by side. I'm supposed to make them touch each other, but I'm leaving some gaps so that you can actually distinguish the lines. You have to understand that they are actually touching each other like the fingers of your hand if you actually close all the fingers without any gap in between. And then you give it a certain number of rolls. Let's say you give, let's say 10 rolls over here of the with the string, and then you give a mark over here, and then you, let's say you give one mark over here, and then you give another mark right over here. So you know that within these two mark of the string you have exactly 10 rolls. Then you unwrap the string out of this pencil, and then you hold it against a meter rule. Let's say this is a meter rule, and you hold the you straighten up this string, and then you hold it against this and against the meter rule in such a way so that your marks are right here and marks are right here. So then you measure how much is the total length. Observe what is happening here. We are trying to measure the diameter of the pencil. This is our question mark. What we just did, let's say if there were 10 wraps, we actually measured 10 times the circumference, right? One whole circular movement gives you what? One circumference, right?
জি স্যার
Now we are going to measure this circumference using the two marks of the string. Now, other than doing it 10 times wrap, if we did only one wrap, then we are going to get one circumference of the whole thing, which would have plus minus 2 millimeter of uncertainty, because we are taking two observations. We have to make two observations, one on the left, one on the right, so 2 millimeter of uncertainty. But because we wrapped it 10 times, so this measurement is giving us 10 times the uncertainty, which also has an uncertainty 10 times the circumference, which also has the uncertainty of still 2 millimeter, because we still made our observation on two different points. The beauty is that if I now divide this thing by 10, if I divide this whole thing by 10 to get the single uncertainty, we're gonna get the uncertainty plus or minus 2 millimeter equals to this measurement. Let's say this is our length L. This would be L divided by 10. So this thing would also actually I messed up the calculation. দাঁড়াও, ক্যালকুলেশনটা লিখতে ভুল করছি আমি আমি জিনিসটা একটু গুছাই লিখতেছি। Why can't I pick the eraser?
Sir, is Microsoft Whiteboard better than Paint?
Yeah, I'd say so. For most part it is, but for certain operation it can prove to be a bit difficult. For example, when I'm trying to draw rectangular lines, it many times it makes them into boxes, so that can be difficult sometimes. Anyway, so let's say this whole length is L. So if I write over here that L equals to 10c plus minus, actually I am writing it wrong. what I was trying to write is that the 10 times the circumference equals to the measured length from the meter rule plus or minus 2 millimeter. এখন ঠিক আছে, এই কেসে ছিল হচ্ছে if we had only one wrap, then the circumference would have an uncertainty of plus or minus 2 millimeter. But whenever we have 10 times wrap, then 10 times a circumference would give us this much. So that way, a single circumference would be L over 10, which is 1/10 of the whole measurement. Now this uncertainty will also get divided by 10, which means now you will have an uncertainty of only 0.2 millimeter. What I need you to understand that we use the same device, which is meter rule, which has an uncertainty of how much? 1 millimeter for one observation. But because we chose to do this for 10 rotation, the circumference now has an uncertainty of how much? 0.2. We reduce the uncertainty by significant fraction just because we chose to do the same measurement multiple times. Does the idea make sense? Or in
Yes,
other
sir.
or
Yes,
in other words, I can tell you that this 2 millimeter now got distributed over 10 times the circumference. So each circumference now have an uncertainty of only 1/10 of this 2 millimeter, which is 0.2 millimeter. So if we did 20 wraps over here, this would have been much smaller. If we had 100 wraps over here, this would have been even much smaller. This is the very basic idea why in many experiments we are asked to do repeat and average. This is the exact reason why we are asked to do repeat and average. Think about it. What is the আচ্ছা না টাইমের ব্যাপারটা এখন না বলি, আচ্ছা repeat and average. Repeat and average actually helps in the way that whenever we do one reading multiple times, then the same amount of uncertainty affect all of those readings. But whenever we do the average, then that amount of data actually comes to a much smaller value. Let me give a very simple example. You kids have measured the time for an oscillating pendulum in many of your experiments, right? An oscillating
sir.
object, you
Yes,
are
sir.
measuring the time to
Yes,
measure
sir.
the time period. The minimum number of oscillation allowed for this measurement is 5 for an lab experiment environment. The maximum number of oscillation that we allow is 20. The standard number of oscillation that we recommend is 10, that you observe the oscillation for 10 of full oscillations and record the time with your stopwatch. Now, stopwatches are actually really precise. The smallest fraction or the smallest time any digital stopwatch can measure is 0.01 second, which is the smallest data in the stopwatch display. Let me show you.
স্যার একটা কোয়েশ্চেন ছিল
বলো।
স্যার ওই যে প্লাস মাইনাস 2 মিলিমিটার দিয়েছিলাম কারণ ওই যে ইয়েতে দুইটা মার্ক দিয়েছিলাম ওই যে স্ট্রিং এ
Yes.
জি স্যার ওইটাই কোয়েশ্চেন ছিল যে আই থট দ্য প্লাস মাইনাস 2 মিলিমিটার ওয়াজ বিকজ অফ দ্য
No, we are making two observations over here, one for the left, one for the right. So each of the observation accounts for 1 millimeter of uncertainty. So two observation, 2 millimeters.
জি স্যার বুঝছি স্যার
Beautiful. So এই যে মনে করো এটা হচ্ছে আমাদের একটা টিপিক্যাল স্টপওয়াচ, আমাদের ল্যাবে আমরা যে স্টপওয়াচ গুলো ইউজ করি সেটা হচ্ছে okay, this is good, this is good. So what happens over here, so this is the second mark, so this actually counts seconds. This is the minute value, so this actually counts minutes. So this is actually a stopwatch that can measure up to 9 minutes or something like that, but in some cases we can have a bit bigger. This one on the other hand measures 1/100th of a second, because this can go from 0 to all the way up to 99 and then it comes to 0. So these are stopwatches have a device based uncertainty of only 0.01 second for one reading. But this is something, this uncertainty is not so useful for our purpose. Tell you why. The key source of error that happens in the case of manual time measurement comes from human reaction time. Think about it. The key source of error that happens during time measurement using a stopwatch comes from human reaction time. It means that, let's say you are observing the motion of a pendulum and you are supposed to start the stopwatch at a certain time, and you should count 10 oscillations and you should stop the stopwatch to your best capability at a certain time. But our reaction time actually is the reason why we cannot start and stop at the exact time that we want to start and stop. For a healthy regular human being, the reaction time is considered to be somewhere around 0.4 second. That's the typical average reaction time for a regular human being. I'm saying regular human being means the person is not sleepy, the person is not tired, the person is not intoxicated, the person is not really old, the person does not have any epileptic motion on their muscles. A regular, healthy, well rested, not intoxicated regular human being has a typical average reaction time of 0.4 second. So while starting the stopwatch, we can have an error of 0.4 second. While stopping the stopwatch, we can have an error of 0.4 second. So altogether, whenever we measure any time using a stopwatch, let's say if we are measuring a time of, let's say, t, that measurement is usually errorful by an amount of 0.8 second because of the two individual incidents of start and stop, both of which are susceptible to human reaction time errors. So that's why this small time value that the device can accommodate, 0.01 second, is not usually the uncertainty for digital stopwatch. So you have to understand that for the case of meter rule, the uncertainty was coming from the device because there is no such thing as human reaction time. You can take as much time as you need, look at the reading, and you can actually go ahead and take the reading to a very good accuracy for your observation. So 1 millimeter is 1 millimeter. That's why the device limitation is the key factor. Similarly for vernier caliper, similarly for micrometer screw gauge, but not for the case of a stopwatch because human reaction time is something that we cannot overcome while using the stopwatch. However, if we use some other mechanized method of time measurement, for example, light gates, or if we use something like high-speed video camera feed, that's a different issue. But I'm talking about human operated uh, stopwatch, digital stopwatches in this example. So that's the typical uncertainty that we have to deal for the case of a human being. Now, what I need to understand, whenever we measure the oscillation time for 10 oscillations, then 10 times the oscillation gives you that amount of time which you get from a stopwatch plus minus 0.8 second. Whenever you get the oscillation time for 1, then you're going to have divided this number, so whatever that number is, divided by 10 plus or minus 0.08 second. You see, just because we decided to observe 10 oscillations, now we can reduce the uncertainty related to resulting from our reaction time by 10 times. This is a far more acceptable or far more reliable data compared to this one thing. So if we only observe one oscillation, then our data could have been errorful up to 0.8 second. Whereas if we make 10 observation, that data is only errorful up to 0.08 seconds. So that's the whole idea, or that's the whole benefit for repeat and average, that we can minimize the error amount, or we can distribute the single value of error amount over the whole reading. That way the exclusive amount of error or uncertainty for a single reading can become significantly small. Does this idea make sense
Yes, sir.
জি স্যার
so far? বুঝাচ্ছে
Yes,
কিনা?
sir. But sir, can the opposite happen? Like the more readings we take, the more errors it becomes.
For a standard operating principle, it shouldn't happen that way. But then again, for just because you asked me that, same experiment done by different people can always lead up to different set of results. For example, let's say I'm trying to measure the value of G, gravitational acceleration, using a simple pendulum on the same day on the same room, and some other of my students, they said some 10 group of students are also measuring, they're doing the same experiment. It is very much possible that I might have a very far away data from the actual, let's say the lab location has a value of reliable value of G value, G naam ki acceleration due to gravity of, let's say 9.81348. Let's say this is the value of G for our lab experiment value. Now you might wonder, how come we can have this kind of a 5 decimal place data? I mean, how could we do that? Well, it's possible to have this kind of a value, this much precise value that is reliable over a huge statistical output. Let's say I've been doing the experiment of measuring G for a lot of different apparatus data, for a lot of different formula over the last 10 years. Let's say you're in your mastermind school, your physics teacher, Jasmine Miss, has been doing this experiment for a really long time. If she wanted to have a really good measurement of the value of G, what she could have done, or what if I was a lab teacher, I could have done is that I could keep record of all the G values calculated by the experiment of all the students and have a total statistical output and eventually get an average of all of those data to get me a reliable value of G at that location. Let's say this is the value of this G. So it is possible that if multiple people are doing this experiment, some people's data can always be a bit on the far end, some people's data can be pretty much on the close end. So multiple readings can lead to more errors if different people are doing this experiment differently, so that they have different level of care and understanding of precision for the experiment, and that can lead up to certain type of errors. For example, one of the important thing that is that you can consider one of the important that you can consider for this aspect can be this example. Let me show you one of these earlier examples that I had. Video call set. Where is this thing? Here. So have a look. When I gave you this example, I told you that whenever we are trying to measure the length of a certain object using emitter rule, if the object's length actually falls in between the two lines of a millimeter scale, we can either choose this value, we can choose this value. This is actually true. For the sake of consistency, for consistency's sake, what is a real recommended way is that if you do this kind of a measurement multiple times for a single experiment, you are allowed to choose the first style. For example, let's say on the first case, you choose the value that is somewhat smaller. So you choose the mark that is on the left of the object's alignment. If the object's alignment is perfectly on a certain line, you choose that, no big deal. So there is no question about the accuracy of the reading. But if it falls onto the halfway mark, then let's say first you choose the left one. A recommended procedure to do the remaining of the experiment, that for all the other cases of length measurement, you always choose the smaller one, so that all of your data are somewhat on the smaller side of the actual result. This would give you an idea that whatever your final reading is supposed to be, it is to be somewhat bigger because I chose all the small readings. However, if a certain person actually flips back and forth, for some of the readings they are not careful to choose the smaller reading, for some readings they go for to choose the bigger reading, they make the left and right choice. It is not essentially what can I say, it's not essentially unallowed, but it is not recommended, because that would give you a bit more spread out data, which is gonna lead up to a much more errorful calculated value. Because for some of the reasons you are choosing it to be small, for some of the reasons you are choosing it to be large, so the spread of the whole errorful data is gonna become far too bigger. So the experimental procedure that we're gonna do for the achievement of our result can prove to give us a different set of results in many cases. বুঝতে পারছি?
স্যার
হ্যাঁ বলো।
স্যার আমরা দুইটা রিডিং এর এভারেজ নিতে পারবো না, লাইক মাঝখান তাহলে আরো কমে যাবে না আমাদের
No.
আনসার?
বলতেছি, we are not allowed to do that. That's another one of the other question, that whenever we use a certain measuring equipment, we are limited by the accuracy of the device. Like I said, that if we're using a meter rule, our reading should be in full multiple of millimeters. You cannot take this, I mean, observing this one, you should not write 630.1 millimeter, 630.5 millimeter.
Then
That,
sir, it'd be more inaccurate
it would be fundamentally wrong, because if you assume that this
because
is
it
a
is an assumption.
Yes, exactly, because you're doing an assumption. You are going beyond the capability of your equipment, and you are assuming an accuracy that is not available to you. So you are producing the sense of accurate data that is actually not present. So you are misrepresenting the accuracy of your data, which is not acceptable in a scientific research value. বুঝছো কি বলছি?
Yes sir.
So you are allowed to mention your data with uncertainty. So whatever the equipment that you have, whatever the equipment that you're using, you provide the uncertainty of this device, and that's perfectly all right. You do not have to bring in more accuracy just for the sake of a better experiment. If you require more accuracy, you better develop better precise equipment, or you order those, or you make those. For example, the person who first devised the micrometer screw gauge didn't only make it out of fun. They were trying to reach a much higher value of accuracy, which they couldn't do with vernier caliper. So they went for the circular motion, converted into linear motion, and they went for that accuracy. This idea of micrometer screw gauge using gears and everything can be broken down into far more smaller fraction. I mean, think about it. How does a micrometer screw gauge work? Let's say this micrometer screw gauge, when it rotates one whole cycle, it actually gives you 0.5 millimeter rotation over here, right? Now, if you devise, other than having the handheld device over here, you can make a gear arrangement over here which could give you 1:100 ratio. So you can have a gear ratio over here with another apparatus setup where this whole thing would be placed within a contraption or a physical setup, that rotating the gear handle by one time is gonna make this thing rotate only one division. So you can make a simple concept into a far more precise data, provided you need that. And if you can achieve that, then you should represent your data with that level of precision or that level of small uncertainty. But unless you have that access, no data should be represented with fake or assumed accuracy. That is fundamentally wrong. Does it answer your question?
Yes, sir.
Beautiful. So uncertainty এই কনসেপ্ট নিয়ে কারো কোনো কোশ্চেন আছে কিনা? Anyone else?
স্যার আরেকটা কোশ্চেন ছিল স্যার।
বলো।
স্যার একটা অবজেক্ট যদি একটা মিটার রুলের উপরে বসে আর এই অবজেক্টটার বারবার রিডিং নিয়ে আমার আনসার্টেনটিটা বাড়বে না? লাইক আমি যদি একটা অনেক লম্বা একটা লাইক করি স্ট্রিং এর মতো প্যাচ আর অনেকগুলো সার্কামফারেন্সের রিডিং, তাহলে আমার আনসার্টেনটিটা কমবে। বাট যদি আমি একটা জিনিসের বারবার রিডিং সেম লেন্থ এর increase.
What you're proposing that দাঁড়াও আমি বলতেছি, ছবিটা কেন কোথায় গেল? র্যাপার আচ্ছা এইখানে। So what you're saying that if I do this length measurement, I mean 10C multiple times, you're saying that?
Yes sir, ওইটার একইটার যদি বারবার রিডিং আর বারবার অবজারভেশন নিতেছি তাহলে করবে না স্যার?
This actually can help to reduce to some extent, but in core construct it would not actually affect it that much. I'll show you why. I'll tell you why. Let's say I'm gonna do this reading for the sake of more reliability. I'm gonna do this thing 3 different times with 3 pieces of strings, or same string, but I'm gonna do this 3 different times. So what's gonna happen? Let's say my length 1 is gonna be 10C plus or minus 2 millimeter. My length 2 will be also 10C. Actually I'm ভুল লিখতেছিলাম। For the first reading 10C equals to হবে হচ্ছে length 1 plus or minus 2 millimeter. For second reading 10C would be equals to L2 plus or minus 2 millimeter. For third reading 10C would be equals to L3 plus or minus 2 millimeter. Now if you do the average of it, so you're gonna sum it. So if you do the sum, what are you gonna get? 30 times the circumference equals to L1 plus L2 plus L3 plus or minus 60 millimeter. Sorry, 60 na?
Sir, 6 millimeter.
Plus or minus 6 millimeter. ঠিক আছে? Now once again, if you divide this whole thing for to get a single value of C, this will be what? C equals to this whole thing L1 plus L2 plus L3 divided by 30, which is basically 3 times into 10 plus or minus 6 divided by 30 gives you how much? 0.02. So what I'm trying to show you is that you're gonna have 3 different readings which should be divided by 30 to give you the similar value of C, but your uncertainty is pretty much remaining the same what we got over here as 0.02 millimeter. Where is that value? Where did I write that? Here. No.
So এটা শুধু 0.2 হবে।
0.2 হবে না এটা?
জি স্যার।
আচ্ছা। So 0.2 millimeter. Now, Hassan, what you just asked me is that if we mess up the measurement method in a wrong way without understanding it, let's say it can happen, it's not impossible, then it is possible that a wrong approach towards measuring a certain value can expose us towards a higher amount of uncertainty than we should have had. It is possible that a person can choose a more complicated way of that involves a bigger number of observations that leads to a much bigger amount of error for the bigger amount of uncertainty in the measurement. It's possible, but we try our best not to do that. So hypothetically, if you ask me that, is it possible that multiple readings can lead to more uncertainty? The answer is yes, there is a probability for wrong steps it can happen, but in sane mind we prefer not to do that, if that makes
জি
sense.
স্যার, বুঝছি স্যার।
বুঝে গেছে?
জি স্যার, এইটা দেখে বুঝে গেছি স্যার, ওই যে ইয়েটা।
মানে এই ক্যালকুলেশনটা দেখে বুঝছো?
জি স্যার।
Beautiful. Acha, anyone else? We actually have a lot of kids over here. Many of you are not asking any questions, so I hope it's either making sense or you are just not enjoying this at all. I hope it makes sense.
জি স্যার, ঠিক আছে।
Sir, by means of division, we can actually lower the uncertainty.
Yes, precisely. That's the whole idea behind repeat and average.
Okay, sir.
আচ্ছা, এখন আমি তোমাদেরকে যেটা দেখাবো, সময় আছে কতক্ষণ?
শেষ
স্যার, 11টা
zero।
বাজে স্যার।
আর
হ্যাঁ,
0
সময় শেষ। আচ্ছা ঠিক আছে, শোনো, টুইসডেতে আমি তোমাদেরকে দেখাবো যে কিভাবে আমরা different how can we work with multiple different type of uncertainties, মানে uncertainty related আমাদের কিছু ক্যালকুলেশন আছে, ক্যালকুলেশন গুলা কিভাবে অ্যাপ্রোচ করতে হয়, how can we handle with same type of quantities, for example length and length, how can we, for example if we are trying to measure the density of an object, mass by volume, তো mass হচ্ছে কিলোগ্রাম, এটা একটা আনসার্টেনিটি আসবে, ভলিউম হচ্ছে মিটার কিউব, এটা আরেকটা আনসার্টেনিটি আসবে, তো দুটো তো ডিফারেন্ট কোয়ান্টিটি। সো এই দুটো আনসার্টেনিটিকে যদি আমরা কম্বাইন করে ডেনসিটির একটা কম্বাইন আনসার্টেনিটি দিতে চাই, তাহলে সেই ধরনের কেসে আমরা কিভাবে জিনিসগুলোকে হ্যান্ডেল করব, ঠিক আছে? এই ধরনের কিছু অ্যাপ্রোচ আছে। তারপর মনে করো হচ্ছে যে কিছু কোয়ান্টিটি আছে যে কোয়ান্টিটি গুলোর কোনো ইউনিট নাই, যেমন মনে করো হচ্ছে রিফ্র্যাক্টিভ ইন্ডেক্স, রিফ্র্যাক্টিভ ইন্ডেক্স ইজ গিভেন বাই হোয়াট, সাইন আই বাই সাইন আর, মনে আছে?
জি স্যার।
জি
যেকোনো
স্যার।
একটা রিফ্র্যাক্টিভ ইন্ডেক্স, এটা তো কোনো ইউনিট নাই, তাহলে এই ধরনের কোনো একটা সার্টেন কোয়ান্টিটি যদি হয়, তাহলে এই ধরনের কোয়ান্টিটি আমরা আনসার্টেনিটি কিভাবে মেনশন করব? এই আনসার্টেনিটি আসবে হচ্ছে অ্যাঙ্গেল আনসার্টেনিটির উপর। সো হাউ উড দ্যাট এফেক্ট আওয়ার uncertainty over here?
স্যার,
So
এটা কি আমরা মানে
স্যার,
এখন শিখবো স্যার নাকি ওয়েবসাইট শিখবো?
না না, এই চ্যাপ্টার এই আনসার্টেনিটি ক্যালকুলেশন সব এই চ্যাপ্টারের পার্ট।
ওকে স্যার।
আনসার্টেনিটি টোটাল ক্যালকুলেশন এই চ্যাপ্টারে আমরা শিখবো। সো এই জিনিসগুলা ইনশাআল্লাহ আমরা টিউসডে ক্লাসে আলাপ করব, ঠিক আছে?
স্যার আপনি কি রেকর্ডিং আজকে দিয়ে দিবেন রাত্রেবেলা ইউটিউবে নাকি কালকে?
মোস্ট লাইকলি রাতে আপ করে দিব, কারণ হচ্ছে এই যে এখন ভিডিও স্টপ করার পর রেকর্ডিং প্রসেস হতে জুমে কিছুক্ষণ টাইম লাগবে, তারপর আমি আপ করার পর এইচডি ভার্সন অ্যাভেলেবল করতে ইউটিউবে আবার কিছুক্ষণ টাইম লাগবে। আই এম লুকিং ফরওয়ার্ড টু আপলোড ইট টুনাইট।
স্যার, আপনি কি
Okay,
কোনো
thank you.
ভিডিও এডিটিং করবেন কিছু?
হ্যাঁ?
Will you do any video editing to the recording?
I don't want to.
Okay, sir.
I was careful not to include any weird stuff so that I don't have to do video editing. So yeah, I prefer not to do video editing. Video editing seems to be difficult job.
স্যার পড়া লাগবে না স্যার।
Yes. Pulvan, thank you very much. Thanks for the attention span. And Allah Hafiz. মঙ্গলবার দিন আবার দেখা হবে। আর কারো কোনো কোশ্চেন থাকলে আমাকে বলো। তোমরা আমাকে দেখলে মেসেজ কেউ কেউ মেসেজ পাঠাইছো, ফাইন, আমি মেসেজগুলো রিপ্লাই করার চেষ্টা করব। If you have anything to tell me in person, please contact in the messenger. Assalamu alaikum.
Almost.
আল্লাহ হাফেজ স্যার।